Hello, and welcome to our NLP course. NLP stands for Natural Language Processing, and it's the field of machine learning that primarily deals with text. Text presents a lot of unique challenges in machine learning, the main thing being that it's not very structured. In fact, it's what we would call unstructured data. So we have to come up with a bunch of techniques to deal with and organize text in a way that can be digested and used by machine learning models. Text, like natural language text, has a lot of natural patterns and things that we can exploit about it. So NLP is the study and practice of exploiting those patterns and those things to make machines that can use text as input. Another way to think about NLP is as the intersection between computer science and linguistics. Linguistics historically has played a big role in the development of NLP, and we used a lot of things that we learned from the study of linguistics in order to make machine learning models that take in text. Nowadays, that's becoming less and less the case because neural nets, particularly very large neural nets, learn these patterns on their own. So we don't have to put them in ourselves. But it's still useful to learn these techniques. One, because they're typically computationally a lot more cheap. So in low resource settings or just kind of quick and dirty, get some stuff done. It's good to know about these techniques, but it's also just in general good to know about these techniques to kind of understand, even when you're working with a larger neural net, kind of what it might be thinking, the things that it's learning. So before we go on, I want to do kind of a brief overview of different techniques and things that you can do in NLP and why it's interesting. So we'll be visiting a lot of this as we go along. In fact, a majority of this you will learn about today. But I just want to go through some of the different examples here and get you an idea of like what it is that you can do in NLP. So first things off, we'll do it's topic modeling. So topic modeling is a way of finding structured topics within a large body of text. So say you take the whole body of Wikipedia and you do some topic modeling on it. Some topics that might fall out are like sports and politics, etc. The idea is to try and find structured semantic patterns that you can use to structure your data and organize it into topics and also explore the data. Like if you have a big body of text, you kind of want to know what's in there, just like kind of summarize the topics and like what they are for me. Topic modeling is a great way to do that. Sentiment analysis, this is probably the most common model that is built by beginners because it's really well known and fairly easy to start working on. What sentiment analysis is it's taking a piece of text and it's labeling the sentiment of that text. So a very common one would be tweets. So a tweet would be, I had a great day today, and then that would be labeled positive. I had an okay day today. That was neutral, and I had a terrible day today, that's negative. That's generally how it gets labeled is positive, neutral, negative. But it can get a lot more sophisticated than that. And probably would there's a lot of I've heard of a lot of politicians using this on things like Facebook, etc., with a lot more fine-grained detail of different kinds of emotions and such to understand what's going on. So part of speech tagging, this is trying to structure text according to um, patterns that we're probably already familiar with. So, basic grammar and such. So, so this is a noun, this is a verb, this is an adjective, etc. Not too difficult to explain beyond that, I think. Not much more to it. But if you use POS tagging, you'll probably see a lot of grammar rules that you're unfamiliar with and get very specific. Next is name entity recognition, or it's also called NER tagging. It's very similar to POS tagging. What NER is doing, instead of using just basic grammar, what it's doing is it's labeling people's places and things. So it'll label, for example, if there's some text about Barack Obama, it would say Barack Obama is person, that is a name, but also Barack Obama was a US president. That's an example of name entity recognition. Text summarization, this is taking a big block of text and summarizing it into much smaller text. So take a book, summarize it for me in a page, take a paragraph, summarize it for me in a few sentences. Translation, Google Translate, you should be fairly familiar with this task, taking a foreign language and translating it into another. A more interesting application of this today that's been generating a lot of hype is natural language to code. So describe what it is that you want coded up in plain English or whatever language you choose, and then write the code for me. Um, then we have QA and chatbots. These are very two different tasks in my head. Question answer is I have a question and answer. So Google, you could probably see examples of this if you ask Google a question. Sometimes it'll already pop up what seems like a pre-formulated answer for you. And then chatbots, which is, I mean, you're also probably pretty familiar with this. So think a customer success bot. And these are getting better and better, and it's getting more challenging to recognize when these are human and when these are not. So, what are the tools of NLP? Well, two of them, two very common ones, are Spacy and NLTK. So NLTK stands for Natural Language Toolkit. It's a library from Stanford. This was the default toolkit for a very long time amongst NLP practitioners. It has tons of different great little models that come in for free and lots of text data and examples that you can play with as well. Spacy is kind of a somewhat of a newer kid in the block. Honestly, it's probably getting to be considered old at this point, which is funny to think about because it's still kind of newer-ish to me. But it's a really, really powerful toolkit that is notably much faster than I think any other NLP toolkit out there. It's really well engineered. There's a lot of overlap and functionality between the two. I think we're going to spend more time using Spacy today as that's getting more popular. Um, that these both of these are not state of the art by any means, but you can still get a lot done with just these two libraries. And this is how you would go about installing Spacy and NLTK. It's good to note that in NLP, it's when you're using libraries, you don't always necessarily just install the library and you're good. You often have to download big corpuses of text or even more commonly large language models. So you can see here you have like Python dash M spacey download N, and that's installing the English models and data that Spacey needs in order to um, do what it needs to do in order to use the tools that are available to it. And NLTK has its own kind of package manager as well. So something to be on the lookout for when working with this stuff. It's like, like, hey, I'm getting this warning or it's breaking because it says I haven't downloaded the thing yet. Well, Google and figure out how to download the thing and all will be well. So one of the first things that we have to do in an NLP task is we have to clean up and normalize our text. So what does normalize in the context of text mean? So normalization, let's just talk about what it typically means. Normalization typically is converting high dimensional features into low dimensional features, which are appropriate for an ML model, or it's putting data within a certain range for a model to digest. So text can be represented in a lot of different ways. Like one very common one would be just like uppercase and lowercase. While you and I may read an uppercase word and a lowercase word has like the same semantic meaning, a text model does not. And how we use, casing in like everyday text and such, we think like uppercase is shouting and things like that. This is kind of a pattern and it's often harder for a model to pick up on unless it's a very, very large neural net model. So typically we just kind of strip out that information and just make everything lower or uppercase as it makes it easier for the model to digest and it reduces sparsity in the data. So that's just one example and one way at which text can um, be normalized. There are a lot more, which we will visit in the coming slides, but the general pattern that you want to do is just trying to get a word or a semantic idea in text to be represented by as few tokens as possible. And we'll get more what tokens are in So here's an example of capitalization being mixed and kind of why it's a problem for an NLP model or any model for that matter. So here, skip this is, and just go to sample. I tried recording this previously, talking about the word this, and it made things very confusing. So we're going to see the word sample here. So notice that the sample has mixed capitalization. So it's all capital in the last four letters, whereas in the second block of text after it's been all lowered, it's all lowercase. For every single mixed capital you have here, the model doesn't know that this particular bunching of characters is like the word sample. It has no conceptual idea of what the word sample is, right? It's not a human. It doesn't have any capacity for language, so we have to find ways to teach it. So for particularly non-large neural net models, it's really important, and even for large neural net models, it's important often to make sure that you're just dealing with the same case so that you're representing the same semantic concept with the as few tokens as possible. So the word sample here should only be represented by the word sample. Um, and that should be the case across our entire body of text, is that this should always be lowercase and always be the same thing, because if you change the case anywhere, it suddenly it's suddenly a new word as far as the model is concerned. It has to learn a representation for that word. So to lower text, it's very simple in Python, just text dot lower, and now we have all lowercase text, and we can work with it a lot more easily. So another tool to use to help you kind of quickly clean up and normalize text are regular expressions. What regular expressions are is it's kind of its actually own language in itself to help you select patterns in text and do stuff with that. So, Python, I think the typical string functions that are available to you, they only allow you to like search and replace exact matches typically. What regular expressions allow you to do is look for like much more complicated and kind of abstract patterns. So Python by default has this package RE, which stands for regular expression. And this RE.sub, what it's doing is it's replacing any text that matches this pattern with a blank space. Um, and like I said, this regular expression is kind of its own unique language in a way. So what we have here, and I'll read to what this means, but usually when you're developing a regular expression, you're using like a regex tester. There's like sites you can do where you put in text and kind of iteratively build your regular expression. And I personally am almost always using a cheat sheet. So remember the syntax, because I just don't really have it committed to memory. I remember certain things about it, but usually I'm looking at a cheat sheet to help me build this stuff. So don't bother like memorizing this stuff. Just look up a cheat sheet and build with that. But what's going on here is we have these square brackets, which is like a selection syntax, and then this little caret means not, and then we have A through Z in lowercase, A through Z capital, which in this case isn't necessary because our text is already lower, but 0 through 9. So selecting everything that's not in these range of characters is what this is saying. So everything that's not in lowercase, not in uppercase, and not in 0 through 9. And it's replacing it with a blank space. So that will replace all punctuation and everything outside of just standard characters, etc. Um, so we're removing punctuation here is what's happening. And I mean, really any character that isn't in this range, there's some Chinese in here that would also get removed. But um, basically, the reason why we're removing punctuation here is kind of the same tune as why we want all lowercase is, if we have capitalization, comma, that looks different to a model than just the word capitalization, all lowercase. Anytime you're adding like a new character, it's a new meaning and it has to learn a semantic representation of that particular token. So we want to do whatever we can to make it as standard as possible. So tokenization, you probably already heard me say the word token several times now, and maybe you kind of inferred by context clues that I was talking about words. But tokenization does not necessarily mean just splitting up text into words. It can be other units as well. It's paragraphs, sentences, words, characters, or etc. But whatever you select to be your tokens, it's going to be effectively the base unit feature that your model digests. So that's why most commonly we tokenize into words or like pairs of characters, is because like putting tokenizing into paragraphs, it's going to be hard for a model to learn a representation about a paragraph at like the paragraph level. There's a lot of different ways to write paragraphs, and you see the very, very sparse data. Um, so there's a lot of different ways to tokenize, even like, yes, like tokenizing into words, but you can tokenize into different words in like different ways. Like you can make like first and last names. So say again, like Barack Obama. You could make Barack Obama its own token. So like not Barack token one, Obama token two, but Barack Obama as a single token because it's a single person and a single conceptual idea that we want to represent within our text. So like that would be a common example of when you might be tokenizing every other word in single, but you put certain different tokens and ideas together, so that and represent them with one token to make it easier for a model to learn relationships between things. So we're going to learn a little bit about how to use Spacy to tokenize words and sentences, and they have some kind of good default schemes that you can use. But note that there's a lot of interesting different ways to tokenize, and I suggest that you kind of do up your own reading on this topic to learn kind of the best ways for different use cases and such. So here's how to tokenize using Spacy. I find Spacy to be probably the easiest NLP package to work with because it kind of just does all the work for you without really any thought at all. So here we have from spacy.lang.n import English. And what this English is the kind of English group of models that Spacy uses. So Spacy will have a tokenizer, a tagger, a parser, and NER and word vectors and POS tagging and all kinds of stuff just loaded into this single model. And the great people over at Spacy have selected a good range of models that are kind of good to start with that will organize the text in pretty much every conceivable way that you can think of, outside of like niche cases, right off the bat. And it's really easy. So you do NLP equals English, and this initializes the model. And then we have some text, and we'll say my doc, I underscore doc equals NLP text. And just this single like calling of the model on the document, and it will tokenize your words. It will tag it for POS. It will do NAR tagging. It'll put it into what we call a word vector, which we'll learn more about later. And it just does all the good stuff in kind of one shot. It's really cool. It does it very quickly as well. Um, so then you can kind of go for every token within the document very easily. So you have this very simple syntax where you just like for token in my doc, so it's tokenized already, and you can print out that token list and you can see how it tokenizes. And you can see how it like so some interesting. So it's every word, but some interesting examples is like you will you'll. You see it's separating you and then the apostrophe ll. So we didn't remove punctuation in this case, and it's tokenizing punctuation separately as well. You can kind of get an idea for like how a model might digest these different kind of semantic ideas as a single thing. So like one other idea to make um, this even the tokens even more dense as far as information would be to replace this like YUL with the apostrophe LL with like will, because it's basically the same concept anyways. Yeah, that's how you tokenize with space. So here's an example of some additional customization with Spacy. So here we see this kind of same thing, NLP equals English. And what we're going to do now is we're going to tokenize things into sentences instead of tokens. instead of sorry instead of words. So you do NLP dot add underscore pipe sentenizer. I can't say this word. So what this will do is it tokenizes into sentences instead of words, and you can see all the glorious options that Spacy has available for you on their site. It's really well documented. So they have these kind of default pipelines that are already ready for you. So the Sentenizer, I still don't think I'm saying that right, but is one of the default ones that they have available for you. But you can kind of build your own pipelines as well and introduce your own models and use it within the Spacy framework, which makes things pretty convenient. And then so you add the sentenizer and you document it'll be text and it'll split up your text into sentences as you can see here. So another common thing to do when preparing text for a model is to remove what we call stop words. So stop words are just the most common words typically. So this, and, is, they, their, things like that. So that it's high frequency words that don't carry a lot of information. So depending on what you include in your stop words, you might keep some or not keep others. So sometimes it's useful to keep the word and. Sometimes, I said you remove they or there. Sometimes it's good to keep those words. But generally speaking, for a lot of models, the list of stop words is much larger, particularly for models where order doesn't matter, which is a lot of kind of the older school techniques. For newer neural net models, the concept of stop words kind of goes away because it wants to know every single word in the order that it originally was to understand the full semantic meaning of the sentence. But for a lot of more old school models, um, it's very useful to remove these things as they don't carry a lot of information. We're just kind of like watering down our signal for our model. So here's a very easy way to remove stop words using Spacy. Spacy by default has a list of English stop words that it has, and you can just print some of those out if you want. So here, we're printing the number of stop words. It has 326 in Spacy set, and its first 10 are int. So like, anything that didn't end apostrophe t, so didn't, things like that. While, nor, 15, cannot, himself, across, last, into, make. You get the idea. It's words that just don't contain a lot of semantic information for a particular document. So here's an example of removing stop words. So, we go through the typical Spacy workflow, port our stop words, we have our model, we tokenize it using Spacy, and then we just do a simple for loop, check whether or not the word is a stop word. And, so we have this dot is stop uh, little attribute on a word or a token within our tokenized document from Spacy, and then you just append the words that have been filtered down. So you can see our tokens here. So sample, text, mixed, capitalization, period, want, alter, string, consistent, use, algorithm. What you can see is you're getting words that just carry more semantic meaning than the stop word counterpart. So, the word algorithm, capitalization, analysis, these are the things that, like, if you're to do like a Google search, like, these are the keywords that you would kind of want to pop up if you were looking up for mixed capitalization algorithm or something like that. Did you want to learn more about normalizing text or something of that nature? So lexicon normalization. This is another way of normalizing text. So more commonly, we call this lemmatization, which is probably the most common form of lexicon normalization. So what it's doing is just mapping a words of the same conceptual meaning to what we call a lexeme. So we have these words connect, connection, connecting, connected, and we're all making it the base kind of root word connect. Connect is what we call the lexeme of these words. So they have different meaning when in like spoken language or even written language when word order is preserved. But for a lot of models, we don't really care about this connection, connecting, connected, unless again you're dealing with like a very large model that actually has the capacity to process these little minute differences. So we just swap out all the words with their lexemes, and we have reduced the amount of tokens to semantic meanings. So here's an example of lemmatization within Spacy. So we're loading up a smaller English model this time. It's another way to load models in Spacy. They have different names for their different models. Probably a more common one to experiment with is this ncore web underscore sm, which stands for small. So here we have run, runs, running, runner, runners, and we want to see how Spacy is tokenizing this. So you can actually print out the original word, then you can print out the words dot lemma underscore, and you can see how Spacy is doing run, run. Okay, yeah, makes sense. Runs, then, but the lexeme is run, running, lexeme is run, runner, lexeme is runner, runners, lexeme is runner. So you can kind of see the different choices that Spacy is making when it's lemmatizing different words. It's considering a runner to be different than the word run, which I agree with their choice. So POS tagging, we already talked a little bit about this. POS or part of speech tagging, but as a reminder, part of speech tagging is the process by which we label words as a noun, verb, adjectives, etc. So here we see yet another way that we can load in a Spacy model and underscore core underscore web underscore sm. We just import that after we've downloaded it, and then you can just do dot load to load the model. Then we again, docs equals NLP text. So we tokenize our stuff and run it through the Spacy models. And as I said earlier, with Spacy, it already has scored a lot for you. So it's already labeled all of the parts of speech for our document. And when you go forward in docs, print out the first 8 words of our document, tokens of our document, you can print word.pos underscore to get the part of speech that a word is. So and Spacy has these 3 to 4 letter codes for representing what part of speech a particular word is. So this DEP stands for determiner. Is an AUX. I have my little cheat sheet here. It stands for auxiliary. I didn't do the greatest in grammar in school, clearly. A determiner, sample noun, text noun, with ADP stands for add position. Mixed ADG stands for adjective. There it is. Capitalization is a noun. So you can see kind of different ways you can structure our text according, in this case, to elementary school grammar, which apparently I don't fully remember. But yeah, it's very useful, and you can get a nice refresher on English if you wish as well. So NER tagging or entity detection. So it's recognizing uh, people's, places, things, organizations, etc. So very common things to label for, and this is the list of things that Spacy labels for, is people, including fictional, and NORP, which is nationalities, religion, or political groups, fact, buildings, airports, highways, etc. You can see this list if you Google it for it on Spacy's documentation as well. But these are just a list of things that Spacy has learned to recognize within text, and it'll label those things for you. NER tagging can go well beyond this, and typically NER tagging, I'd say, at least in a professional setting, is typically uh, trained or engineered for a specific use case for a company. Sometimes you get this stuff for free. You're like just looking for people or just looking for these particular entities, but more often than not, you are training a model to identify a particular entity that you're interested in. And Spacy has ways that you can do that fairly easily as well. But for now, we're just going to use what we have out of the box, and because you can do quite a bit with just this. already. So here we have the Spacy example for NER tagging. So it's very similar to the POS example, except because entities can be multiple tokens, Spacy chunks up the entities in a separate attribute called ents, or entities is what that stands for. So if we create a variable New York Times equals NLP, and we have some New York Times text, and then we go through New York Times dot ents, what we'll get back are triplets, which is the name of the actual recognized entity, the entity string code, and then the entity's like numerical label. So we have New York City, which is GPE, which I forget what the actual acronym stands for, but GPE generally stands for just countries, cities, states, etc. Tuesday, it's a date. I think it's pretty self-explanatory. We have at least 285, and we have this thing cardinal. So these stand cardinal is numerals that don't fall under another numeric type, such as like date or something. September, date, Brooklyn, place. I think you get the idea. We Bill de Blasio. He's a person. Orthodox, which is NORP for nationalities, religious or political groups. 6 months old date, up to $1,000 money. So you can kind of get an idea of how this gets useful. But again, typically in commercial practice, um, I think you're more often training your own tagger to find what you're interested in. So here's another way to visualize NER tagging um, in Spacy that has this great little package called Displacy that you can import from Spacy that was done on the previous slide. And you can actually render the style and visualize the different entities that are recognized. You can also do this for POS tagging as well. Yeah, so it's just kind of a prettier way to kind of see the different entities in the text and kind of see what Spacy sees.